Welcome to my YouTube channel, Dhanesh here. So today we are going to discuss about bias and variance. So today our discussion is about bias and variance. Two more topics we are going to cover along with this. One is overfitting. Second one is what is underfitting related to a machine learning model. So four aspects. One is bias, second one variance, third one overfitting, fourth one underfitting. Four aspects here we are going to cover in this video. See, first thing you want to understand, a machine learning model, we used it for prediction. So this is the one important aspect you need to understand. Our machine learning model is used for prediction. So the data we are giving, there are two types of data. These things you already know. Data can be classified into two. One is the training data, and the second part we call it as the testing data. Training data is also known as labeled data. Labeled means it is, for example, the data we are having is the photos of some animals. Then if it is marked, this is horse, this is lion, this is tiger, that is labeled. So then that data we call it as the labeled data. If it is not labeled, then it is known as the testing data, or we call it as unlabeled data. So this is about this. Data is classified into two. One is the training data, the second one is the testing data, and labeled data or unlabeled data. See, normally when we get the data set, 80% of the data we will consider it as the training. We split the data into two parts. One is the training and another one is the testing. The split will be like 80% will be normally 80% will be the training, and 20% will be the testing. In that way we usually split the data. For example, if you want to check whether an email is spam or not, using the subject line, email body, and sender's email address, then these data, whatever you are getting, you will split it into two. The training data should be 80%, and we will test the data, that is 20%, and the machine learning model has to do the prediction based on the testing data or the unlabeled data. So these aspects you are already familiar. Now we are coming into bias and variance. So we are going to discuss about bias and variance. See, to understand bias and variance, a machine learning model, we use it for prediction, and if this predicted value is not equal to the expected value or actual value, there is error in our prediction. So normally the error is denoted by cost function. These topics we already covered. You can see it in the previous videos. Cost function is equal to predicted value minus expected value, predicted minus expected or actual value. This is cost function. See, this cost function denotes error. Cost function is related to machine learning, artificial intelligence, even economics, statistics, all these branches of science. This cost function is coming into picture. But now see, our discussion is towards bias and variance. See, what is bias and variance means? See, our machine learning model once we come up with a machine learning model, we use the training data. See, we have two data sets. One is the training data. This training data will be used for training the machine learning model. After training the machine learning model, we use this model for testing the data. There, the model has to do the prediction on the testing data. See, when we use the training data, for example, I already told 80% of our data from the data set, we use 80% for training data. See, we have, for example, we have height and weight. This is our graph. In this height and weight, so we are coming up with a model. So first we are plotting the training data. See, for particular value of height, this is the weight. So we are plotting the training data. This our training data. This is the first plot. We got it as 1 second. I will give you more. We will do it better. So our first point is, this is our first point. For a particular value of height, this is the weight, and the second, all this red color denotes the training data, and this is the second point, this is the third point, and this is the fourth point, this is the fifth point. I will elongate this graph so that you will get more idea on this. So I am the x-axis, I am extending this x-axis. So this is the plot. See, I have very minimal points I have drawn in the graph. Sorry. So this red points you need to understand. This denote the training data set. I already communicated to you. 80% of the data we will consider for training data. See, if we come up with a model, so you can come up with a model like this. This is a straight line. So when we use this model, this is a linear regression line. If you are familiar with maths, you know the equation of this line is denoted by y is equal to mx plus c, where in mathematics, m is the slope and c is the y-intercept. Here c is 0. And in machine learning or in deep learning or in neural networks, this m we usually denote it as weight and c as the bias. Anyway, in most simple way, or in the basic concepts, based on, if it is the in the most fundamental way, we can tell m as the slope of this line and c as the y-intercept. So this is a linear regression line, and this line gives error. See, this is the actual point. So how much error, for example, this point, how much error it is giving? This much error. The line predicts this value. So this is the error. So error means this predicted value minus this actual value. This is the actual value. This is actual value. And this is this is the predicted value by our machine learning model. Our machine learning model is a linear regression line, and that gives an error. So this difference, there is a based on towards the training data set, our model is having this much bias. So it is having a high bias. I can tell our training data, towards the training data set, our model is giving an error. Here also it's giving an error. See, here also it's giving an error. So in this, here also it's giving an error. So that means our training, towards the training data set, our model is having a high bias. This model is having a high bias. So this is about bias. See, again, I am coming up with, so this is a first degree equation. This model, whatever we discussed, it is a first degree equation and it's giving a high bias towards the training data set. Now, for the same training data, I am giving, I am considering another model. For example, towards this is also for the training data set. So I am using the red color here. So our points again I am plotting here. This is the first point, this is the second point, this is the third point, fourth point, like this. So I am coming up with another model. This is a curved line. Always the curved line is represented by polynomials or second degree or third degree equations. For example, y is equal to x square. This defines a parabola. You know it in math. Y is equal to x square denotes a parabola. So when we consider this line, see, it is, what is the bias here? When you consider when you consider the predicted value and the actual value, it coincides. See, this model gives the error is very less. The difference between the predicted value and the actual value is very less. It passed through the data points. When you consider the training data sets, here it is height and here it is weight. See, it passed through the data points. That means the predicted value minus actual value is very less. So this model, this polynomial, this curved line gives a low bias. And low bias, and this model, when it considers the training data set, it is overfitting. It is completely fitting through the training data set. Low bias and overfitting. So this is the concept of low bias and overfitting. So bias is defined with the training data set. So the first model, whatever we discussed previously, the linear regression line, this model is giving a high bias. So the previous model, it was giving a high bias, and this is giving a high bias. And this graph, we can call it as underfitting. It is underfitting. So this is the concept of overfitting, underfitting, and low bias and high bias. So this graph previously, whatever we discussed, the linear regression model, it gives a high bias and it is underfitting for the training data set, but the curved line or the polynomial model, which is having a low bias towards the training data set, and that model is overfitting. So we come up with two models. One is the linear regression line and polynomial. So we have two models, and these models are ready based on the training data, and we are using these two machine learning models to test the data. We are using these models for testing data. See, in that case, I am the testing data, I am using it with green color. So I am using both the models for the testing data. So for example, first I am using our model, the linear regression line, for the testing data. So our testing data is, the plot is like this. This is the plot for the testing data. So when we give the when we used the linear regression model for the testing data, this much here we use for the testing data, that error we call it as the variance. When we comes to the testing data, that error, we call it as variance, but I can tell you this, it is relatively low variance. Even though this linear regression line, it is giving a high bias for the training data, it is giving a low variance, it is giving a low variance for the testing data, it's giving a low variance. Very important, low variance for the testing data. For the same thing, I am using it for the uh, for this testing data, I am using the second model. The second model is our curved line. So when I use that model, this model was like this, it was like this. You can see here, this model, it is giving, when you consider this data set, it's giving very high variance. This is the error for the testing data set. It was for the training data set, this model was overfitting, but it is giving, when I used it for the testing, when this model is used for testing, it's giving a high variance. See, for this data, it's giving this much variance, and the variance it is giving for the testing data set, this model here, it is if we plot it properly, this much variance it's giving. So our polynomial or the curved line, it giving a high variance for the testing data set. So we usually define the variance for the testing. So I can give you more clarity. The variance we usually define for testing data. Bias we define for training data. This is important. So our first line, the linear regression model, it's giving a high bias, and when it used it for testing, it's giving relatively low variance. But our polynomial, our second degree equation, the curved line was giving low bias, and it was overfitting, perfectly fitting the training data, but it is giving a high variance for the testing data. See, what is the optimum model? See, the optimum, the perfect an ideal machine learning model, it would be like its cost function. I already error, right? Previously I told you the error is denoted by cost function. It is not a complex term, it is a simple term only. Cost function means the simplest equation I can give you for cost function is predicted minus expected, but there is different equations with root mean square, mean square equation, and modulus. You will calculate the modulus and find out different equations are there. For the time being, you can understand like it is a cost function, it is predicted minus expected, and this, for an ideal model, the cost function, that is error, must be minimum. So we need to find out the minimum of the cost function. That means here you need to understand, to minimize the error, you need to understand like the bias and variance. So for an ideal machine learning model, it must be having low bias and low variance. Here comes the optimization between bias and variance. So that is the bias variance trade-off. So we need to optimize the bias and variance. So for that we need to optimize the machine learning model and come up with a low bias and low variance, then only our prediction will be correct. That means the error is low. So that's what we need to understand here. So for that purpose, we have different approaches in machine learning for optimizing the bias and variance. To get into low bias and low variance, we have different approaches. One is the ensembler method. So for reducing the bias, for to getting low bias and low variance, or optimizing the bias and variance, we have different methods. One is known as the ensembler method. Ensembler method is classified into two. One is boosting, second one is bagging. So there are two methods for ensembler method. The second one is the regularization. This is another method. We use it for optimizing the bias and variance. Regularization is a mathematical approach. See that we usually use it in statistics as well. Regularization, we introduce some constants, and we have some functions we introduce, and it's a mathematical approach. So that is regularization. We will be coming up with new videos for regularization as well. So these are all the approaches we usually use to optimize the bias and variance. One is the ensembler method. Ensembler method is of two types. One is boosting and bagging. The second one is regularization. So this is all about bias and variance trade-off. Thanks for watching.